Hello, everyone. Okay, now let's go on to part two of gases, where we talk about um, the ideal gas law in a little bit more detail. Okay, so when we talk about gas laws, they ask us to predict what happens when one or more changes are made in the variables that describe the gas. So we've been using this equation based on the fact that these variables are equal to some constant, and and that has to do with how gases behave, and that's the constant R. So, but if we just break it down to the individual gas laws, we can see that the product of a set of variables, for example, Boyle's law, pressure and volume, that will equal one, that will equal a certain value. And when we change the value of one of the variables, the resulting final pressure and also the the volume. So say we changed, not just change one, but change a set of variables, increase one and then decrease the other, or sorry, no, like if we do keep we change one of the variables, right, and we're asked to predict how would the second variable change, right? So if both sides are equal, they must equal to the same constant. So that's why we can set them equal to each other and solve for one of the unknown variables, and then we get the equality here: P1 V1 equals P2 V2. Okay. So likewise, we can also do this for a set of conditions of for the ideal gas law. So we could say the initial conditions of a gas with P1, V1, N1, T1 is also equal to the conditions of the gas at time 2, or instance where we change the variables. All right. So we can substitute known values here of pressure, temperature, and volume, and amount of gas into the equation and solve for one unknown. So let's do that right now. So assume a sample of ammonia gas fills a 27-liter container at negative 50 degrees Celsius and 2.58 ATMs. So let's calculate the volume of the gas at 21 degrees and 751 millimeters of mercury. Okay, so let's list what we have. We know about the system. So P1 is 2.58 ATM. V1 is 27 liters. And temperature 1 is negative 15 degrees Celsius. We don't know the amount of gas in either case, so we're going to put a question mark there. And then here, this should be P2. So for P2, we have 751 millimeters mercury. Okay. V2, we do not know V2, but we know temperature 2 is raised to 21 degrees Celsius. Okay. So we have three unknowns in this equation. Okay, so we have three unknowns in this equation, right? So we have three unknowns in this equation. So that's first now, but before we begin, let's convert it to consistent units. So 2.58 ATM. So let's convert the second pressure into ATMs as well. 0.988. Okay, 27 liters. 258 Kelvin. We still don't know N1 or N2 or V2. And for T2, we now have a new temperature of 294 Kelvin. Okay. So now we can substitute this information in the two equation. So P1 V1 over N1 T1, okay, equals P2 V2 over N2, oops, not that, N2 T2. Okay. So here we now are going to plug in what we know. So P1 is 2.58 atmospheres times 27 liters over N1 times 258 Kelvin. (294 kelvins here). Okay. So right now we have 3 variables we haven't been able to solve. But we recognize that N1 is equal to N2. Okay? It's because the amount of ammonia has not changed. Okay? So we can cancel those out. In this case, they will equal each other, right? So they will cancel out because we can cancel out the variables if we multiply both sides by either one of those variables. So that will cancel out. So now it becomes more simpler. So we can now rearrange the equations to read V2 equals 2.58 atmospheres times 27.0 liters times 294 Kelvin over 258 Kelvin times 0.988 atmospheres. So if we look at some of the variables here, we notice that the temperature is increasing, and so the volume there, it should increase. And then we see the pressure is also, but the pressure is also decreasing, so the volume should decrease. So depending on the ratio of the temperature and the two pressures, one of those factors will dominate predominate in terms of our calculation, and then our volume 2 could either be higher than volume 1 or lower than volume 1. And in this case, if we compare the ratio of the pressures here, 2.58 divided by 0.988, that's about 2.6. And if we do 294 divided by 258, that's going to also, oh wait, sorry, I was mistaken. So you see here both the ratio of the pressures here. So we look at the ratio of the pressures. It's going to a lower pressure, so volume should increase. And then if we look at the temperature is increasing, so temperature should also cause the volume to increase. So we should see an increase in volume as our final answer. And if we calculate this, we get to a final volume of 80.3 liters. So we were correct. So if you think about the variables and how the gases should behave in an ideal situation, you can verify your answer to be most likely correct, and you're kind of not like hoping that the answer is correct and that you did everything right in the equation. So if you kind of think of it conceptually, you can also be more confident in your answer. Okay? All right, let's move on. All right, so let's answer this question here. According to the calculation, the volume of the gas should increase. from 27.0 liters at negative 15 degrees Celsius and 3 atm to 80.3 liters at 21 degrees Celsius and 751 millimeters of mercury. Okay? So that's how we would finalize our answer here. Okay. Let's move on. All right. Now let's talk about Daltons Law of partial pressures. So gases, we typically say, okay, gases, they don't like to pretty much interact with each other because they're moving so fast. So we can say that the pressure of a gas is proportional to the number of moles of the gas if the temperature and volume are held constant. So we just have a container in we just have a vessel, and the temperature and volume are held constant. The pressure will be proportional to the number of moles of gas. It will just be proportional to the number of moles, and that if there's a mixture, the total pressure results from each component. And then each component contributes a partial pressure. So we can actually just add the sums of the partial pressures, and we get the total pressure of our system. Okay, so let's put that into a word problem here. So let's calculate the total pressure of a mixture that contains 1 gram of hydrogen, 1 gram of helium, in a 500 liter container at 21 degrees Celsius. So let's list what we have. So volume is 5 liters. Okay. And the temperature is 21 degrees Celsius. So we're going to convert that to Kelvin. Equals 294 Kelvin. All right. So the first thing is we need to solve for pressure, right? We need to find the pressure. So to solve for pressure, we would take pressure of hydrogen equals nRT over V. So first we need to solve for moles, right? Because to find pressure, we need a number of moles, but luckily we have grams. So in this case, we have 1.00 grams of hydrogen. Okay. And now we know that for 1 mole of hydrogen, we have approximately 2.02 grams of hydrogen. Okay. And if we do that math there, we can get 0.495 moles of hydrogen. Okay, so if we do, sorry about that, I lost my train of thought for a minute. Okay, maybe because it's raining really hard outside, but I'm glad the heat stopped. I didn't expect it to get this cold so quickly. It kind of switched gears like a switch. Okay, so there we have the moles of hydrogen, but let's also calculate the pressure for helium as well. So the pressure of helium would be the moles of helium times RT over V. And maybe let's rewrite this equation so it's easier to see here. So it's well, not easier to see, but easier to represent. So it's clear that you need to find the moles of hydrogen. So we have 1 gram of helium. Measuring out gases, though, is kind of difficult because gases are moving so fast. So it's really hard to approximate the mass of such gases. So I guess how you did this in the lab is you would get a syringe and you would estimate the volume of the gas, and you'll using the density of each gas, you can figure out the grams you need based on the volume you have. That's how I would think people would do experiments like this. I've never studied gases in such a way here, but it's kind of interesting, like how far chemistry has become and how they did this. Because just handling gases is not easy. It's kind of a pain. So 1 mole helium, and handling gases can be quite dangerous as well. 4 grams of helium. Okay. So if we do that calculation, we get 0.250 mole helium. Okay. So now if we solve the PV equal to nRT equation, we get pressure is equal to nRT over V. So let's solve for the pressure for hydrogen first. Equals. So for hydrogen, we have 0.495 moles of hydrogen times the gas constant, 0.8206 liters ATM. Mole Kelvin. Okay, and the temperature here is going to be 294 Kelvin. And then the volume here is 5 liters. So on a test, you probably do want to show all your calculations so you can get most of the points for partial credit. So if you do show the work and you do get the final answer you wrote is wrong, if you just write the answer, I can't actually give you partial credit because I don't know how you got to the answer. But if you show me how you set up the equation and you set it up right and you just made a calculation error, I can still give you most of the points for the question. So I encourage everyone to always show their work. Or to write something that shows you understand how to solve the problem. So we get moles of helium now. Same kind of deal here. Okay, and we solve this, we get 1.21 ATM. Okay. So now if we were to calculate the total pressure, we add them up. So P total equals pressure of hydrogen which equals 2.39 plus 1.21, which equals 3.60 ATM. So this would be your final answer. There you go. Okay. So that's how you do a partial pressure calculation. So common question in chemistry, I would say, on calculating partial pressure, given the masses of 2 elements, and you have to use the ideal gas law. Okay, so let's move on to the next part of our discussion here on gases. Okay, so how did Dalton kind of derive this? Well, so he studied, he saw this pressure based on his work, based on the fact that there's some water vapor that collects after he's based on some experiments he did with studying air gases and water vapor. He found that water vapor could be absorbed by air at different temperatures. So what his law does, it often is used to correct for the amount of water vapor when you're studying gases in solution, or when you're doing reactions and you're collecting the gas. Usually you collect it over water because it's easier to collect it that way instead of just pouring it into a empty container. Okay. So he often, what he found out is that the partial pressure is often a combination of the pressure of the gas you're looking at and also the amount of water vapor that was absorbed by the air. Okay. So these gases are not very soluble. So what you can do is you can actually invert a flask underneath, submerged in water, and then what happens is the gas will just go into the empty vessel, and due to gravity, it can't go back because it's not very soluble. And since there's always a stream of air probably bubbling through, it'll stay at the bottom of the bottle there. And to prevent it from escaping, you would cap the bottle underwater. Okay, so that's how we would measure or how we could get obtain gas from chemical reaction. For example, potassium chlorate, and it readily decomposes the oxygen, so it's a great way to generate oxygen when heated. Okay, so let's answer a few questions. Why doesn't any more water flow through and fill the bottle? Okay, because why isn't water going through to the bottle? Because the pressure of oxygen will balance the atmospheric pressure pushing down on the water. So here's the atmosphere or air, atmosphere / air. Pushing down on the surface of the water. But however, when the pressures are equal here, when the pressure of oxygen plus water is equal to the pressure of the atmosphere, you have an equilibrium state, and now no more water is going to fill. So that's how you tell when. So eventually, if you increase the amount of gas being put into the vessel, eventually the gas will push down onto the water and make it fill, occupy more volume. So eventually you reach an equilibrium state. But if you were able to somehow increase the pressure, you probably push more water out of the vessel there. But in this case, it will reach a point where it will no longer fill up with water. Okay, so let's stop there. We'll pick up in the next video, but that's basically partial pressures for gases. Okay.